G'day everyone, and welcome to our first lesson on magnets. In this lesson, we're going to examine the reasoning that leads to our understanding about what a magnetic field is and the way a magnetic field points around a magnet. So first of all, imagine it's 2,000 years ago and you come across a bit of metal that's a magnet. You can't see the magnetic field, but you notice when you put it in a bunch of metal shavings, which you've shaved off your sword or off a pot, the metal shavings tend to line up in interesting ways. This particular shape there. And when they line up, they're moving. So you're thinking, this bit of metal is exerting some kind of invisible force on those bits of metal. You know there is a magnetic field around that magnet. There's something going on around that magnet at a distance. There's no physical contact between the metal filings and the magnet, but still the magnet is affecting them somehow. Let's use the analogy of gravity. How do you know there's a gravitational field around an object? Well, if you jumped from a great height anywhere near the Earth, you're going to fall to Earth. So we'd say, okay, the gravitational field around the Earth, if that green block is a very bad representation of the Earth, that is the gravitational field. We put arrows in the direction that you'd be pulled if you were released around the Earth there. A magnetic field. How can we test to see the shape of a magnetic field? Well, we can introduce another magnet, say a compass. And a compass has a needle with a north and a south end. So we'll say the north pole of the compass points the geographical north pole of the Earth. There. And we can move the compass. Sorry, I'll be clear about this. We can place the compass at various places around the magnet. And we can see where the needle of the compass wants to point at those locations. So this compass here, the needle might point that way. This compass here, this one here, the needle will point that way. That way, that way, that way, and that way. So we start to see, okay, the needle wants to point away from this end. This needle is pointing away, this needle is even pointing away from that end. But the needles tend to want to point towards this end here. So we can say this magnet has a north pole, which repels the north pole of the compass magnet, and a south pole. So all magnets are dipoles. We have a north and a south pole, and like poles repel, so the north pole here repels the north pole of the magnet, and opposite poles attract. So the north pole of the magnet is attracted to the south pole of this magnet over here. Instead of placing pictures of compasses around the magnet, we can draw magnetic field lines. And the general rule is you draw them in loops. So a magnetic field line is a loop like that, and they get very, very big. And also they cannot cross. Now, using our explanation we've just gone through, we can see why they don't cross. So if, for instance, I had a magnetic field line there and another one here, the magnetic field lines are supposed to show the direction which a compass needle would point if you place it on that field line. So there and here. If I placed a compass along that crossing point there, it doesn't make any sense that the magnetic field lines would cross, because that's confusing. It's telling me the needle of the magnet will point there or there. No, that's not right. The needle of the magnet is going to point in a single direction. It's not going to have this uncertainty in the direction it's pointing. So our magnetic field lines, if we know they have to be in loops, they can't cross, and they point in the direction of a compass needle placed on the line, we can say, okay, there'd be a big magnetic field line running through here. And the arrows show the direction. Compass needles point towards south and away from north. There would also be a big loop going like this, showing the compass needles pointing in that direction there, and below here. So since this magnet is symmetrical, there's some nice symmetry going on. And we draw the magnetic field lines going through the magnet because we know even though we can't physically shove a compass through this metal, there is a magnetic field still inside that magnet there. And if we did embed a magnet in there from the beginning, the field line, the needle would point in that direction there. So I'll fill in the last magnetic field line I'm going to draw. Just a few loops there. In motion, we discussed the difference between scalars and vectors. A scalar is something like speed. It simply has size. So you say I'm going 60 kilometers an hour. That's just the size of the speed. There's no information in a scalar about direction. A magnetic field is not a scalar. A magnetic field is a vector. And because it's a vector, it has both size and direction. Now look here. It's very clear the direction of these vectors. Like the vector of the magnetic field here is in this direction. But the size of the vector here is not clear. You have to infer, so you have to understand the size of the magnetic vector around a magnet increases when the lines get close together, and it decreases when the lines get further apart. This should agree with your everyday experience. If I took two magnets and put them here, two north poles together, it's very hard to close this gap. It's easier to close the gap if the gap is big. It's easier to go from a big gap to a smaller gap, but if the magnets are very close, like this, closing that last gap there by forcing these magnets together with your hands is very, very difficult. Because as you push them together, the lines here get very, very close together, and there's a large magnetic field which is repelling one magnet from another. Let's look at the magnet inside the Earth. Whoops. Don't want to scale. I want to rotate. So the Earth, we'll approximate it with this blue line, acts like a giant magnet. I think I may have put these last few arrows on wrong. So the north arrows have to go that way. Yeah, I may have got that wrong. That looked a bit funny. Anyway, I'll rotate this around again. Rotate here. Then I'll draw the Earth in. Okay, apologies for getting the direction of these arrows wrong before. So we can use compasses on the Earth. We take a compass, it has a needle, it points towards geographical north. So we'll say this is geographical north. And this would be geographical south. The Arctic and the Antarctic. But notice, the geographical north corresponds to the magnetic south pole of the Earth. And that makes sense because pretend you had a compass on the surface of the Earth here. The north pole of the compass needle is not going to point towards the magnetic north pole of the Earth, like poles repel. The magnetic north pole of the compass needle is going to point towards the magnetic south pole of the Earth. That's why this line here will line up with the compass needle. So just remember the magnetic pole here and the geographic pole are opposites when it comes to the Earth. Now a little explanation for why magnetism exists. Any bit of metal has atoms and electrons. The electrons have, well, if not motion, they definitely have some kind of spin. And the motion slash configuration of the electrons creates little magnetic fields in the metal that point all over the place like that. Every atom will have its own little magnetic field. If you can somehow make all those magnetic fields line up in the same direction, they sum together and you get a really big magnetic field going on, as we just saw before. This kind of lining up can be induced in a bit of metal. So say we already have a magnet here, and then I've got a little bit of metal over here. This magnet has magnetic field lines coming out of it, going like that. And those magnetic field lines act together to make the magnetic fields in this bit of metal line up like that. So the north pole of this magnet repels the north pole of each of the little, we say, domains inside this magnet. So this metal over here becomes a magnet in the presence of this magnet here. If we then remove this magnet and we find this magnet over here maintains its electric field, we say it was a soft metal. If we remove this magnet and the magnetic field inside this magnet and outside disappears, we say it was a hard metal. So you can see how many of the magnets we use were created. You can simply induce a magnetic field in a new metal by putting it in just in the presence of a magnet you already had. And this also shows us why magnets, we saw at the start, actually attract metal. Before we said, there's something going on with the magnet that distinguishes it from any other bit of metal. Because when you chuck it in a bunch of metal filings, they line up like this. What's actually happening is each of these metal filings is becoming its own little magnet.